Everyone. So this lesson gets more into this idea of writing integrals as functions. And these first two examples really are things that you have already done. We get into maybe using some integral notation a little bit more with them, but you've already done these questions in the first lesson in this chapter. So I'm going to kind of buzz through these pretty quickly. The real new stuff is what happens on the back of this page. So that's kind of the important part of this lesson. But okay, so example one, we're starting with a velocity function. Says I want to use a midpoint Riemann sum. Notice that I'm only going from 10 to 70, so the 0 and the 80 I actually don't need. I'm starting at 10 and going to 70. And I'm doing a midpoint Riemann sum, which means when I make my intervals, I want to hop over a number in the middle. So I want one interval to go from 10 to 30, and you'll notice that 20 is the midpoint between 10 and 30. I want my other interval to go from 30 to 50. And again, you'll notice that 40 is the midpoint between 30 and 50. And then 50 to 70 with 60 as the midpoint. And so the width of each one of these intervals is equal to 20. All of my widths are the same here. This is 20, this is 20, and this is 20. And then what I'm using as the height of my rectangle is the y coordinate, the velocity value, at the midpoint. So I'm going to use the 22, and I'm going to use the 35, and I'm going to use the 44. Okay, and so I am going to use an integral notation here. And I'm going to say this is from 10 to 70 of v of t. And we are approximating because we're using a Riemann sum. Um, and I'm going to do this because all of my widths are the same. I'm going to cheat a little bit here and just put 120 on the outside here and then do 22 plus 35 plus 44. That only works if they all are the same width. If they were three different widths, I'd have to write them all separately. But if you think about this in terms of distributive property, this is really saying 20 times 22 and 20 times 35 and then 20 times 44. Okay. Let me do this math real quick. Sorry, I wasn't prepared with a calculator here. 22 plus 35. I might have to cheat and use the phone here. Okay, here we go. 20 times 22 plus 35 plus 44. And I get an area of 2020. Now, I didn't give you a unit on my velocity, but this would be total in whatever measurement my units were in. It's not a rate of change. Okay, so if this were inches, then this would be 2020 inches. If it was meters, it would be 2020 meters. Oh, and then I should have read ahead. Write your answer using integral notation. Well, that's what I just did, right? So my integral notation is just this thing right here. Okay, saying that we found the integral from 10 to 70. Um, and in terms of the context of the problem, remember that when you do this Riemann sum where you're adding up the area, anytime you're just finding the areas and adding them together, technically what you're finding is the displacement. And it's the displacement from t equals 10 to t equals 70. And I'm using the word displacement very carefully here because what I know for sure, well, it's an estimate, so I guess I don't know it totally for sure, but I know that from 10 minutes to 70 minutes, or whatever these happen to be, maybe they're seconds, 10 seconds to 70 seconds, my position changed by this much. Now, for all I know, I was turning around and running backwards and then ran forwards again. And, maybe I was running back and forth a whole bunch. But if I compare starting position to ending position, the difference is 2020 units. Okay. And again, that unit would be whatever your velocity was being measured in. I just didn't give you units to work with here. So, all in all, that was not a very well written problem for you. So, sorry about that. But the math is still good. Okay, so here's another situation where I'm given velocity, and this time I'm given it on a graph. This is a bug crawling on a picnic table. At least I gave you units this time, inches per minute. And I want to know how far did the bug end up from its initial position. Well, if I integrate a velocity function, that's what I'm finding, right? Is I'm finding how far did the bug actually travel. So let's find some areas here. This is a trapezoid with a base of 6, and then this base looks like it goes from, let's see, 3 would be here. So that's 3 to 5. So this is a base of 2. This is a base of 6 with a height of 3. So 1/2 times 3 and then times 2 plus 6 is what I'm seeing here. Hope I'm counting that right. So that's 24 and then times 1/2. So this has an area of 12. Okay, get rid of my other numbers here just so I don't confuse myself later. My radius on this circle goes from 10 out to 14. So that's a radius of 4. And so my area here would be pi times 4 squared. And then remember, it is a semicircle, so it's living underground. So that's 16 pi divided by 2. So I'm going to say that this is 8 pi. And then here I have a triangle with a base that goes from 14 out to 22. So that's a base of 8. And it looks like my height goes up to 8 as well. So my area is going to be 1/2 times 8 times 8. So that 64 divided by 2 is 32. Okay, so for how far did I end up? This is telling me that I was moving 12 inches to the right over this time period. So from 0 minutes to 6 minutes, I went 12 inches to the right. This now is underground, right? And so as I'm moving from left to right, this would represent negative position change. So it means I'm moving to the left. So I'm going to subtract 8 pi. And then here I'm moving back to the right again. So I'm going to add another 32. And so I would put this all together just by combining the 32 and the 12. And so I'm going to say 44 minus 8 pi, and then it would be inches. And since this will end up being a positive answer, this tells me that my initial position shifted to the right, okay, because this does come out to be positive. So from time 0 to 22 minutes, the bug moved this far to the right, okay, the beginning position to end position. Now, how far did the little bug's legs actually walk? Well, this part that we counted as being negative before, that's still distance, right? It's just moving in an opposite direction. That's why we subtracted it before. But if all I care about is like total distance that I traveled, what I want to do is I want to consider this as just being positive. So if I'm looking at total distance, we want to just make everything positive, okay? And so all that's going to change about my answer is now I'm going to say 12, and then I moved 8 pi, and then I moved 32, and so I would say 44 plus 8 pi inches. That's how far the poor little bug's legs actually walked. Okay, like I said, you've seen all of that before. I do think on the other side here, right up at the top, I do have kind of a summary of what we just talked about, which is if I'm asking you about the change in position, and this is another way of saying displacement, we're just going to integrate the velocity function. But if I ask you about total distance, then what I want to do is take that velocity function and just pretend everything's positive. And that's easy to do when you're on a graph and you can just turn things into being positive. When you do these with like equation functions, you can use absolute value to take all of your areas and put them above the x-axis. Okay. So I'm going to stop this video here because again, that stuff was all really review, and this example 3 is really kind of the meat of this lesson. So I want to make sure we spend a good amount of time focused on that. So I will pick up with that one in a second video.